This is a length of plastic pipe. Buried in the ground behind a house, it delivers air at around 55 degrees on the hottest afternoon of the year, continuously, with no refrigerant, no compressor, and nothing running except a small fan. Europeans have a name for it. They call it a Canadian well, and it appears in serious passive house design across the continent. In North America, it is usually called an earth tube. And here's the honest part stated up front, because the title makes a big claim, and I am not going to leave it hanging. This does not replace an air conditioner in a hot, humid climate. It cannot, and I will show you exactly why in a few minutes, because there is a genuine failure mode here that most videos on this subject skip entirely. What it does is dramatically reduce the work your cooling system has to do, for essentially nothing, forever. In the right climate, it can carry a house on its own. In the wrong one, it will grow mold in your pipe and make you ill. Knowing which climate you're in is worth more than the pipe, and I will give you the test. Let me start with the physics, because it rests on one fact that most people have never had explained. Dig down into the ground and the temperature stops changing. At the surface, soil swings enormously. It bakes in July and freezes in January. Go down a foot, and that swing is smaller. Go down a few feet, and it is smaller still and delayed, so the ground down there is warmest in autumn rather than midsummer. Go down about 10 to 20 feet, and the swing effectively disappears. At that depth, the soil sits at roughly the average annual air temperature for your location all year round, and it does not care what today is doing. Across much of the United States, that number lands somewhere between 50 and 60 degrees Fahrenheit. Sit with what that means. On a day when the air outside is 95, the ground 8 feet beneath your lawn is 55. That 55-degree mass is enormous. It is free, it is already there, and it is doing absolutely nothing. An earth tube is simply a way of putting your air in contact with it. You bury a long run of pipe at that depth, draw outside air in one end, and by the time that air reaches the other end, it has given up its heat to the soil. It arrives in your house at something close to ground temperature. You are not making cold. You're borrowing it from the largest thermal mass on your property. Now, the history, because this is not a modern idea by any measure, Persian architecture used it centuries ago, pairing underground channels with the tall windcatcher towers you see in desert cities. Air was drawn down into cool subterranean passages, sometimes across water, and delivered into the building. Those systems cooled buildings in genuinely brutal desert climates with no machinery at all. European farmhouses used cellars and buried ducts for the same purpose, long before refrigeration existed. And the modern version has a European name because it never really went away there. The Canadian well is standard vocabulary in passive house design, and thousands of European homes have one built in as a matter of course. In North America, the technique nearly vanished for the reason everything in this series vanishes. Air conditioning arrived, it was cheap, it worked instantly, and it worked in any climate, regardless of design. So builders stopped designing houses that cooled themselves and started fitting machines that did it for them. This channel exists for exactly this kind of straight answer, one honest method a week, and subscribing is how those keep arriving. Now the arithmetic, so you know what you're actually getting. The output of an earth tube depends on three things: the length of pipe, the diameter, and the airspeed through it. Longer pipe means more contact time and cooler delivered air. A wider pipe means more volume moved but less contact with the walls per unit of air. Faster air means more volume and less cooling. A typical residential installation runs somewhere between 100 and 200 feet of 6 to 8 inch pipe, buried 6 to 10 feet down. That will deliver air within a few degrees of ground temperature at a moderate flow, and the volume is genuinely useful. Here is the honest comparison, though. An air conditioner produces cold air, often in the mid-40s at the vent, and it dehumidifies aggressively as it does so. An earth tube produces cool air in the 50s, and it does not dehumidify at all. Those are different products. If you walk to an earth tube vent expecting the blast of an air conditioner, you will be disappointed. What you get instead is a large, continuous volume of air that is 30 or 40 degrees cooler than the air outside, delivered for the cost of running a small fan, which might draw 50 to 100 watts against the 2,000 to 4,000 watts a central air conditioner pulls. That is the trade. Less dramatic cooling at roughly 1/40th of the running cost. And there is a second half to this that almost nobody mentions, which is winter. The ground is 55 degrees in January, exactly as it is in July, because that is the whole point of the depth. So on a morning when the air outside is 15 degrees, that same pipe delivers air at 55. Your heating system is then warming incoming air from 55, rather than from 15, which is a 40-degree head start on every cubic foot of fresh air the house takes in. That matters more than it sounds, because a well-sealed modern house still needs ventilation, and every bit of cold air it draws in has to be heated. Pre-warming it with the ground is genuinely valuable. So the same buried pipe cools in summer and preheats in winter, without changing a single thing about the installation. It is one of the very few systems in this entire field that works in both directions, with no modification at all, and in the right climate, that is genuinely enough. In the dry heat of the American Southwest, the interior West, and much of the high plains, a well-built earth tube can carry a house through summer with the air conditioner barely running. Which brings me to the part that decides everything. Humidity. Here is the failure mode, and it is the reason I would not let you build this without hearing it. When warm, humid air passes through a cold pipe, water condenses on the pipe walls. That is unavoidable physics, exactly like a cold glass sweating on a summer day. Now you have a long, dark, buried tube with standing moisture in it, at a comfortable temperature, with air blowing through it into your house. That is an ideal environment for mold and bacteria, and you have built a system that delivers whatever grows in there directly into your living space. This is the reason earth tubes have a mixed reputation, and it is the reason installations in humid climates have genuinely caused indoor air quality problems. So the honest map is straightforward. If you live somewhere with dry summer heat, meaning the desert Southwest, the interior West, the mountain states, or much of the high plains, this technology is close to unbeatable, and it is exactly where those Persian systems were built. If you live along the Gulf Coast, through the humid southeast, or anywhere summer air arrives loaded with moisture, an open-loop earth tube blowing outside air into your house is the wrong system. And no amount of good construction changes the dew point. There is a version for humid climates, and it is worth knowing. Instead of drawing outside air through the pipe, you run a closed loop, circulating indoor air through the buried pipe and back, so you are cooling air that has already been dehumidified, rather than importing wet air from outside. You lose the fresh air benefit, you keep the cooling, and you avoid the condensation problem almost entirely. The closed-loop version is the one I would build in a humid region, and almost nobody mentions it. Now the build. The pipe is your main material. Smooth-walled plastic pipe in 6 to 8 inch diameter is standard, and smooth matters since corrugated pipe traps water in every ridge and is far harder to clean. Expect this to be the largest single cost, priced by the foot. Depth is the next decision, and deeper is better up to a point. 6 feet is a workable minimum. 8 to 10 feet is where the ground temperature is genuinely stable, and beyond that, the digging cost climbs faster than the benefit. Length determines your output, and 100 to 200 feet is the usual residential range. If your ground allows, a serpentine layout in a trench gets that length into a modest footprint. Slope is the detail people skip and then regret. The pipe must be laid at a consistent fall, so condensate runs to one point and drains, either into a sump, a dry well, or daylight. A flat pipe holds water permanently, and a pipe holding water is the mold problem you are trying to avoid. The intake needs to be well above ground, ideally a few feet up, screened against insects and rodents, and filtered. Put it away from driveways, dryer vents, and anywhere pesticides are used, since whatever the intake smells, your house will smell. The outlet enters the house, usually into a plenum or a central room, and you need a fan somewhere in the system to move the air, since the pipe will not draw usefully on its own in most designs. And you need cleanouts, access points at each end, at minimum, so the pipe can be inspected and flushed. A buried tube you cannot get into is a buried tube you cannot maintain. Total cost varies enormously depending on whether you have access to an excavator, since the trenching is the expensive part and the pipe itself is comparatively cheap. Doing it during an existing excavation, such as a new build or a foundation dig, is dramatically cheaper than digging specifically for it. Now the limits, all of them. The first is the humidity problem I have already given you, and it is the deciding factor. The second is that it does not dehumidify, which in a muggy climate means the house can feel cool and clammy rather than comfortable. The third is that the ground itself can saturate. Continuously pulling heat into the soil around the pipe warms that soil over a long hot season, and performance drops toward the end of summer. The ground recovers over winter, but a system size too small will fade in August. The fourth is that retrofitting is expensive, since digging a trench across an established garden costs far more than laying pipe during a build. The fifth is maintenance, which is real. Inspect the intake, check the drainage, and flush the pipe periodically. And the sixth is radon, which deserves its own sentence. In regions with elevated radon in the soil, an underground air pathway into your home is a genuine consideration, and the answer is to test your home for radon and to seal the system properly, which is standard practice anyway. The safety picture is otherwise mild. There is no electrical hazard beyond an ordinary fan, no pressure, no combustion, and no chemistry. Screen the intake properly, because an open pipe into a house is an invitation to rodents, insects, and small animals, and dealing with something dead in a buried pipe is exactly as unpleasant as it sounds. Never route the tube through ground you suspect is contaminated, near a fuel tank, or under a driveway where oils leach. And if you have a solid fuel appliance or any combustion appliance in the house, remember that any system moving air changes the pressure balance of the building, so a carbon monoxide alarm is not optional. That is true, regardless of this project. The ledger for the whole story then. Pipe, priced by the foot, and the main material cost. Fan, $30 to $150. Intake structure, screening and filter, $30 to $80. Cleanouts and drainage fittings, $20 to $60. Excavation, which is either free with a machine you already have on site or the single biggest line on the list. Here's the thing worth keeping from all of it. 8 feet under your lawn, there is a mass of earth sitting at 55 degrees, all summer, every summer, and it has been doing that since long before your house existed. Persian architects built entire cooling systems around it in a desert with no machinery whatsoever. And European builders still design houses that use it as a matter of routine. North America mostly stopped, not because it failed, but because a machine arrived that worked in any climate, in any badly designed house, at the flick of a switch. The ground did not go anywhere. It is still 55 degrees down there, right now, under your feet, doing nothing at all. Everything this channel has gathered on cooling a house without the grid, the loops, the stores, the real numbers, and the real limits lives in one place, linked right below. And the comments are the missing map. What state are you in? And are your summers dry or muggy? That single answer decides whether this belongs on your property or not, and I read everyone. As for the barrel of ice that shifts your air conditioning off the afternoon peak and still works in 30 years, that is on screen right now. Same enemy, different approach. Till next time.